bone is not dead. It is one of the most biologically active tissues in your entire body, constantly being broken down and rebuilt every single day of your life. Right now, as you watch this, specialized cells inside your bones are dismantling old bone and building new bone simultaneously, in a process called bone remodeling. Your skeleton replaces itself completely every 10 years. Every single bone you have today is younger than a decade old. But when a bone breaks, this same biological machinery shifts into emergency mode, performing one of the most extraordinary feats of natural repair in all of medicine. Today, we go inside a broken bone, in full 3D anatomy, to watch every stage of the healing process from the very first second of fracture to complete restoration. To understand how bone heals, we first need to understand what bone actually is. Compact cortical bone, the dense outer shell, is organized into cylindrical units called osteons, or Haversian systems. Inside each osteon, osteocytes, the most abundant bone cell, form an extraordinary communication network through tiny channels called canaliculi. Cancellous bone, the spongy inner architecture, is a three-dimensional lattice of trabeculae aligned precisely along stress lines to maximize strength with minimal material. The periosteum, the fibrous membrane covering bone, contains the stem cells that will be the heroes of bone healing. Bone has an extraordinary blood supply, and it is the disruption of this blood supply that makes fracture healing both challenging and remarkable. The moment a bone breaks, a cascade of biological events begins within milliseconds. Blood vessels inside the bone and periosteum are torn, flooding the fracture gap with blood. Within minutes, this blood begins to clot, forming a fracture hematoma, the first and most critical scaffold of bone healing. This hematoma is not just a blood clot. It is a biological signaling factory packed with growth factors that will orchestrate the entire healing process. Within hours, the inflammatory response arrives. Neutrophils and macrophages flood the fracture site, clearing debris and releasing more signaling molecules. The dead bone at the fracture ends, deprived of blood supply, is progressively removed by osteoclasts over the following days. Simultaneously, new blood vessels begin growing into the hematoma through a process called angiogenesis. Without this vascular invasion, healing cannot proceed. By day 3 to 5, the inflammatory phase transitions into the reparative phase, the most extraordinary stage of bone healing. Now, the most remarkable transformation in bone healing begins, the formation of the soft callus. Mesenchymal stem cells from the periosteum and bone marrow migrate into the repair zone and make a critical decision based on oxygen levels. In the oxygen-poor central zone, stem cells become chondrocytes, producing a cartilage scaffold through a process called endochondral ossification. The cartilage callus is temporary, but essential. It provides mechanical stability, while the more permanent bone callus forms around it. The hypertrophic chondrocytes at the center of the callus now begin mineralizing their surrounding matrix. The first bone mineral is being deposited. Simultaneously, osteoblasts are laying down woven bone directly on the periosteal surface, forming the hard outer shell of the callus. The blood supply continues to expand throughout the soft callus, and as oxygen levels rise in the central zone, chondrocytes give way to osteoblasts. By week 3 to 4, the fracture is now bridged by woven bone. It is not strong yet, but the fracture is no longer mobile. The woven bone callus now enters the third stage, mineralization and hardening into the hard callus. The hard callus is stronger than the original bone in some ways, but it is architecturally disorganized. The collagen fibers run in random directions rather than the precise parallel arrangement of normal bone. Now the fourth and final stage begins, remodeling. This is when the disorganized woven bone is slowly replaced by perfectly organized lamella bone. Osteoclasts carve tunnels through the callus, and osteoblasts follow behind, laying down perfect concentric rings of lamella bone, rebuilding new osteons one by one. The bone responds to mechanical stress during remodeling, using the electrical signals generated by bone deformation to guide where new bone is placed. Over months, the excess callus is progressively removed, and the bone returns to its original shape and diameter, precisely reconstructed to meet its mechanical demands. The speed and quality of bone healing varies enormously between individuals, and the reasons why are now well understood. Age is the most significant factor. Young bone heals dramatically faster because it contains more stem cells and has a richer blood supply. Smoking is one of the most damaging habits for bone healing. It reduces blood flow to the fracture site by up to 40% and impairs osteoblast function. Calcium and vitamin D are absolutely essential for bone healing. Calcium provides the mineral, and vitamin D enables its absorption from the gut. Mechanical loading, controlled weight bearing, actually accelerates fracture healing by stimulating osteoblast activity and optimizing callus formation. When healing goes wrong, a condition called non-union can occur, where the fracture fails to heal after 9 months. Modern medicine can now accelerate bone healing using ultrasound, electrical stimulation, and biological agents including bone morphogenetic proteins. Your bone is not passive material. It is a living, sensing, self-repairing masterpiece of biological engineering, capable of rebuilding itself from complete fracture to full strength.